everything? All right. Yeah. I can imagine that today we're gonna kind of need to take it a little bit slow, kind of be chill. Don't want to like give you like 20 reactions. The first one we're gonna do today, we're gonna wrap up chapter 16, and we're going to do the Wittig reaction. Yay! And this one is kind of similar to the Grignard reaction in that first we're going to make the Wittig reagent and then we're going to do the Wittig reaction. So making the Wittig reagent. And another name for the Wittig reagent is the Halide. So Wittig reagent, aka the Halide. And let me zoom in for you guys just a tad. Better? So when we're making the Wittig reagent, we are going to start with an alkyl halide. So let's just say this. Cool. Like 25 reactions this semester have started with an alkyl halide. The important thing is the reagent. So when we're making the Halide, there's two sets of reagents. So in the first step, we have PH3. And this is going to go in and essentially replace the halogen. So we get bam, bam, PH3. And we have a positive charge on the P. In the next step, we have C6H5Li. What's that? Ta-da! And this is just a strong base. Just because phosphorus likes to have 3 bonds, and then when it has 4, it has a plus charge. Well, it likes to have either 3 or 5 bonds, but we'll see that in a second. Okay. So at this point, what we're going to do is we're going to steal this hydrogen right here. So the base will come in, steal that H, and give those electrons back to that carbon. And I'm going to scoot over just a tad, but I'll zoom out at the end. Bam. So now the hydrogen is gone. So we're left with a lone pair on the carbon. And then we have a bond to phosphorus, which has a plus charge. And then it's attached to pH3. At this point, we have 2 charges. So what we can do is resonance. We can pop this over and get bam. Oh, yes. Thank you for letting me know. And now our charges are happy. And we're going to put a little bracket around here to indicate that these guys are resonance structures of one another. And the name is the Halide. So if you ever see an alkyl halide and then you have 2 arrows, one is PPH3 and one is C6H5Li, you know that we're making the Halide. And we know that that is part of the Wittig reaction. So that's going to be a dead giveaway. If you ever see those things, you're doing the Wittig reaction. PPH3. If you ever see PPH3, dead giveaway, Wittig reaction. You'll see. Okay, so I'm going to show you the actual Wittig reaction and how to do it, and then I'm going to show you the rosemary method to do it. The rosemary method is my favorite. Okay. So let's just give this a little heading. The Wittig reaction. Okay, so the Wittig reaction is going to be between a carbonyl group and the ylide. So for the carbonyl group, I'm just going to draw a general structure. Let's call it R1 and R2. And this could be an aldehyde. So the H's, the R groups could also be H's. And then we're going to react that with an ylide. So I'm going to say R3, R4, because again, these could be any carbon chains. And it's double bonded PPH3. And I'm sorry, I'm going to draw the other resonance structure just because I think that's easier to see. Again, both of them are the ylide, it's just a different structure. Yeah, you can see either one. It's just easier to show you the mechanism if I draw it this way. All right, so in the first step, let me also move this negative sign. In the first step, these electrons are going to come and attack here. And then these electrons go up to the oxygen. And I'll draw it like all as one thing. This goes back and attacks the phosphorus. Double welcome. Okay, so now we get this weird box structure type thing, and I'm going to keep it as consistent and similar as I can. So this carbon has R1 and R2 on it, and that now has a bond to this carbon, which had R3 and R4 on it. And then we have a bond to phosphorus, which is bonded to three phenols. And that is bonded to the oxygen. So we have this really weird looking box intermediate, right? And at this point, oxygen and phosphorus are really attracted to one another, and they kind of don't care about carbon anymore, so they're going to throw away carbon. So what happens is this bond breaks, electrons go to the oxygen, then oxygen makes a double bond, which breaks this pink bond and gives those electrons to that carbon. And what carbon is going to do with those electrons is create a double bond here. So we're essentially breaking apart the box. And I'm just going to do it underneath. So on one side, or one of the products, we get O double bonded to PPH3. And the other product, which is the more important product, is R1 and R2. I will move it up in 1 second. Double bonded to R3 and R4. Ta-da! Who loves this reaction? Okay, one person, not the norm, but that's okay. All right, so let's do it the fun way. I'll give you like 1 more second to write stuff down. Yes. Yes. So essentially what's going to happen here is this bond is going to break, or let's start from here just because it'll make more sense. The oxygen wants to make a double bond to this guy, right? Once it makes a double bond, these electrons are going to be kicked away from the phosphorus and to the carbon. Carbon doesn't want to have a negative charge, so it's going to use those electrons to form a double bond. And that double bond is going to break this one, because then it'll be 5 bonds. So it starts out with the oxygen making 1 bond, and that breaks this one, makes this one, breaks this one. Yes. That's a good way of thinking about it. Okay. So I'm going to add another page. Okay, chill. So we're going to do the rosemary method. Okay. Are you ready? I don't think you're ready. I'm ready. Okay. So we're going to have some kind of carbonyl, R1, R2, and we're going to have our ylide, R3, R4. Looks pretty much the same right now, but we're not just any regular old boring chemists, right? We're biologists, most of us. So you know what we're going to do? We're going to get a little bit too excited about Halloween, and we're going to become Dr. Frankenstein for a second, okay? So we got these two things, and we want to make completely different creatures. And since we're freaks, we're going to take the 2 heads, and we're going to see what happens when we put them together. So this is a little molecule creature. This is a little molecule creature. This is the head. We're going to decapitate it. Bam. This is another molecule. This is its head. We decapitate it. Bam. And again, we're freaks of nature, and we want to know what happens if a molecule creature has 2 heads. So, O, CH3. No, just kidding. CPH3, right? And then we're like, oh darn, we're all out of heads. So what else can we make? And then we're like, all right, what if there's a molecule creature that doesn't have a head? It's just arms and legs, right? So we're gonna take the arms of this creature and the legs of this creature. We're just gonna stick them together. So we get arms and we get legs. Thank you. The best part is, okay, right? I have arms that can go this way, or my arms can go this way. Same thing with my legs, they can go this way or that way, right? So when we're making the new creature, R1 and R2, if they're arms, you can stick them on this way, or you can stick them on this way, and you can mix and match. So I can put my legs this way, my arms that way. But what I can't do is I can't replace one of my legs with one of my arms, because that's just too weird, right? So we can't flip-flop R1 and R3 or R1 and R4, but we can do this and this as much as we want. Okay? Cool. So if we were to flip those around, so let's say I had this, and I also had R2, R1, R3, R4. What is their relationship to each other? Starts with an S. Stereoisomers. Cool. Ta-da! So what you can always do for this reaction basically is just take the arms and the legs of the 2 groups and just stick them together. And then your side product is always going to be OPPH3, but that's kind of garbage. We don't care about it. I got so excited, I started like hyperventilating a little bit. The little things, man. Questions about this reaction? Cool. So we are going to do some practice on it. And also I want to mention this reaction has a question that shows up on your exam. It's like the weirdest formatted question I've ever seen. So we're definitely going to practice that right now. And if it looks confusing, I know. It's okay. We got this. All right. So it's going to look something like what's an oxidizing agent we could use here? PCC. Cool. Or we could use literally any strong reagent. That would also work. And then I'm going to give you something weird like this, right? Does this look like it makes any sense? No, not really. I'm actually just going to make one teeny tiny change to it. It'll have this last arrow right here. All right. So basically what this means is that there's one reaction up here. So this is reaction 1. There's one reaction here. That's reaction 2. And then the products of those 2 reactions are being added together to make reaction 3. So there's 3 completely separate reactions going on. So the one on top, they give you the starting material, the reagent, and the product. So there's nothing for you to do there, right? All you care about is this guy, because that's the product that goes into reaction 3. So if we were to kind of redraw it so it looks better for our minds, we would have this ketone like this. So the second reactant for reaction 3 is going to be whatever is formed here, right? So PPH3 plus C6H5Li tells us that what reaction are we doing? What? Yeah, well, yes, it's the Wittig, but specifically, we're just making the Ilin in reaction 2. So we could either do this the long way, or we could do it my way. So how I like to look at it is, in the first step to get to A, all you do is you replace Cl with PPH3. And then in the second step, you form a double bond. So I'm just going to say this guy, double bond PPH3. And that's going to be product B. So any question of how I got here? Sort of kind of okay? Yeah. Oh, maybe not. There we go. So for reaction 3, the second reactant we have is the Halide. So if he's asking you for C, this is what you're looking for. Just that reaction in the corner. And if we have a carbonyl plus an Halide, what kind of reaction is this? You guys kind of said it before. The the Wittig reaction. Cool. So I'm going to zoom in. I'll zoom back out at the end. So this is the Wittig reaction. And all we're doing is cutting off the arms and legs, right? So we have two methyl groups attached to one carbon. And on the other carbon, we have one methyl and one ethyl. So ta-da, this would be product C. And I can zoom out so you can see the whole thing. There we go. There is 99% of the time a question that looks like this. There might be a different reagent at the top. He might ask you for B. Or the other thing he can do for the Wittig is retrosynthesis. So if we're okay with this, I would like to try some retrosynthesis questions. Yes. So no, yes, but that's not what he's going to ask you for. So that's going to always be a product, but it's never going to be like the answer, if that makes sense. I see some people writing, so I'm going to let it be for a second. Also, while you are writing, I will mention, exam review is going to be this Friday from 3 to 6. Your exam isn't until next Friday, though. Roche's exam is on Tuesday, so we decided to do it kind of early. I'm going to do another review for you guys, probably during the Wednesday tutoring session, just so it's like a refresher. But I will get back to you at the exact time by the end of this week. I think it's like Veterans Day or something. But he does absolutely hate his students. But that's besides the point. Yeah. West also hates his students. No kidding. He's chill. Doesn't hate you guys. Okay, a couple of new people, not new people, but a couple people did come in late. So I do want to just give you guys a chance to sign in right quick. Let me stop. That was really weird of me to decide to do. I don't know what took over me for a second, but it's fine. This thing doesn't turn off. I feel like it wastes so much electricity. Just 24/7 being on. Could you? Thank you. And then if you're not able to sign in, just like send me an email. This is Ty or something. Sign you in. I don't really care that much about attendance, but my bosses do. Seems like everyone's good. So let's go back. I don't know if I have any Wittig reaction examples in here. Looks like I don't. That's sad. Okay. So for a retrosynthesis example, he could do it a couple different ways. So the easiest would be, let's say he gives you something like this. Yes, so this is going to be Wittig retrosynthesis. So if all he gives you is something like this, and he says, what reagents could we use to make this product? He's not specifying which side was the phosphorus and which side was the oxygen. So essentially what you do is you go to the double bonds. You know that the double bond is going to be split this way because, again, you can't break apart those carbons and mix and match them. You can only match it this way. So there's going to be two options, right? You could have either had this. Sorry. That was so pleasant. Okay, you could have had these two reagents, or you could have had it flipped the other way. And you have no idea which one of these is correct because he didn't give you anything else to start with, only the final product. So he could either give you this set in the answer choices or this set. He can't give you both if he's asking for which two react together. Or he could give you all four of these choices and say which of the following are possible ilids that created this product, right? So now he's saying all of the possible ilids only. So both this, sorry, bless you, both this and this would be correct answers because both of those could possibly be the ilid. How does that feel so far? Okay-ish? Yes. So if he were to ask you which set of reagents make this product, you would either pick these two or these two. They wouldn't, both sets wouldn't be there for you to choose from because they're both correct. Or he could ask you which of the following could be the ilid that forms this product. And at that point, this one and this one could both be correct answers because he didn't specify which side would come from the ilid and which side came from the alpha halide. You're welcome. Mm-hmm. So yeah, I can also set up. Yes. Yes. Ahead. Nice. I love that. So, the first time I did SI for this class, I was so like epic nerd mode. So I actually made it like a meme where I took the Iliad and the Odyssey and I changed the like cover of it to have an Ilid instead of like whatever's on the cover. Dr. S lost his mind. He was like, "Why did you do this?" I was like, "I have a lot of time." Anyways, quirky. Sorry, I'm in a mood today. All right, I'm just gonna go back here and copy this because I don't want to redraw the whole thing. Actually, I lied. I am gonna redraw it. Okay. The other type of question he could have here is, let's just say, yeah. Okay. A. B. C6. A5. I don't know. Okay. So the other way you could ask you a retrosynthesis question is like this. So this is the ugly format that I showed you just now for the forwards reaction. But now he gives you the product and he's going to ask you for either A, B, or C. B is kind of useless to ask you about, so he's going to either ask you about A or C. So the way we would move backwards in this reaction is, oops, I don't know why I did that. So we have this, and we know from the one that we did previously, this is one reaction, this is two reaction, and then this is the third reaction. So we know that this product was formed by this and this. And we also know that the Wittig reaction just takes the arms and the legs and sticks them together. So right off the bat, we can see which side is the arm, right? So we split up this double bond just like we did for the last example. And I can match R1 and R2 to R1 and R2. So I'm going to highlight that right here. And we know this side comes from the carbonyl. So that means this side had to come from the Halide. So now let's work backwards. So I'm going to zoom in at the bottom here. So if we go backwards, we know that the Halide, before it turns into the product, looks like this. And then if we go backwards again, we know that where that double bonded PPH3 was, there had to be some halogen. There's no way of you or for you to tell which halogen it was, so I'm just going to give you an X. So if we zoom out, this guy is going to be C, and this guy is going to be A. And then if for some reason he asks you for B, which he's never done before, all you would do is remove the double bond and put a plus charge on the P. Yes. Oh my gosh, you're so right. I'm sorry. You are so right. There you go. I was looking at it just now. I was like, why is there a double bond? And then you said it at the same time. I was like, there it is. Yay. And I'll also write here, this is the alkyl halide, and this is the Halide. I know this is a kind of weird setup, and this is like not the easiest reaction in the world. So, any questions? It's an Li. Okay, so we're gonna do like a little check-in because this was the end of chapter 16, the last part of 16. So for chapter 16, I'm going to say a 0 is I absolutely hated it with everything inside me. It was the worst thing in the world. 5 is I have it down. I could take the exam right now and get 100. How'd you guys feel? Yep. Okay, so I don't see any like zeros, which is awesome. I saw mostly like 2s and 3s, which is really, really great because we just finished it. Are there any specific questions or things you want to review or things you would like to practice more this week for your exam? If you don't have any on the top of your mind right now, send me an email because I do want to like make the review as interactive and helpful as possible. So let me know. Okay. If there's no questions right now, I do kind of want to get into chapter 17 because I know that will also be on your exam. We have a little bit of time. Oh, that's fine. I don't have it open either, so actually. I'm not even going to turn it off because whatever. Nope, that's not what I wanted. That's what I wanted. Nope, that's not what I wanted. Okie dokie. So chapter 17, we're not going to go like too crazy into this yet because like we don't have that much time and I don't want to overwhelm anyone. We're going to start out with naming and reactivity. So we kind of talked about this in the last chapter, we put some things in order. And we also know the names of most of these molecules. So let's go from left to right. I'm going to point at something and you tell me what its name is. So bam. Yep. What about this one? Ester. What about this one? Amide. What about this guy? This is a new one. Yes. Okay, so it's an acid halide. There's also another name for it, but acid halide is like the most commonly used one. Okay, what about the next one? This is another weird one. Remember? Yes, thioester. So the thio comes from this sulfur group, and ester is because it looks like an ester. Okay, the last one, the weirdest one. Any idea? Close. Yes. So when I said close, not at all, but you know. Yay, the acid anhydride, or we could just call it an anhydride. Depends on the day. And bless you, I think. Means we have one, or actually I'll say A, B, C, D, E, F. And we're going to put it in order of most reactive to least reactive. I believe Dr. West went over this last time in lecture. So what do you guys think is the most reactive one? I think last class we started it, but he didn't get like too deep. Like this kind of. Okay, think back to what we talked about for reactivity in the last chapter. What two things really like determine reactivity? Okay, what umbrella is that one under? Electronics. Oh, darn it, I gave the other one away. Resonance and induction. And the other one was sterics. Cool. So the steric effects for these guys are pretty similar. So let's talk about resonance and induction. So first things first, only one of these groups have an electron withdrawing group on it. Which one do we think it is? The acid halide, exactly. So all of these other guys have a lone pair. And acid halide is just a halogen. So that one is a withdrawing group. So this is the most reactive one. All right. So the next thing we want to look at is we're between oxygen, sulfur, nitrogen. So if anyone has a periodic table or they remember it, which one is the most electronegative? Between oxygen, sulfur, and nitrogen. Oxygen, cool. So the next most reactive will be oxygen. So we're between carboxylic acid, ester, and anhydride. So which one of these guys looks like it has the best leading group? The anhydride. So I'm going to say BAM for most reactive. And then ester and carboxylic acid. Do you remember what we said about those? Not necessarily the lowest. Oh, yes. Okay, so carboxylic acid is slightly higher, but they're almost the same. So we're going to put A before B, but they're approximately the same. And then cool. Between sulfur and nitrogen, which one is the most electronegative? Sulfur. Cool. So the thioester is next. And then last but not least, we have C, which is the amide. So amides are super, 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 super stable in this kind of reaction. So these guys are super reactive, super stable. And in lecture last time, Dr. West said that the reactions in this chapter are not reversible, which is one of those things where it's like, depends on the textbook or like the professor. So for this semester, we're going to say that these reactions are not reversible. And the reason it's not reversible, according to Dr. West, is that the products that we make are often much more stable than the reagents. And so just based on stability effects, we don't want to go backwards. And that kind of answers this question on the bottom. So nucleophilic acyl substitution reactions typically go from what? More to less reactive. Cool. All right, so does anyone remember what was like the reaction title for chapter 16? What? Yeah, it was nucleophilic addition reaction, whereas this one is nucleophilic acyl substitution reaction. So kind of a hint on how chapter 16 and 17 are different. Another thing that you notice is what was the electrophile for every single reaction in chapter 16? What? A carbonyl, but more specifically, ketone or aldehyde. Cool. So these guys are going to be the electrophiles for chapter 17. Do you notice anything different about them compared to aldehydes and ketones? Heteroatoms can be what kind of groups? That's an L. I heard some people whispering it. Yes, leaving groups. So the biggest difference I want you guys to take note of between chapter 16 and 17 is all of these guys have leaving groups. Whereas in chapter 16, we did not. The closest thing we came to a leaving group was an elimination rate in the key. All right. The conceptual stuff is still kind of the same. Like, what do acid catalysts do? Okay, I'm standing here. That okay? Ready? Reset. Reset. How does the acid catalyze affect the reaction? It makes the electrophile more electrophilic. Cool. So how does the base catalyst affect the reaction? Nucleophile more nucleophilic. Yay! No, it's Monday, guys. Come on. Okay. And yeah, I don't want to go into any of this stuff. We could just name esters right quick. So naming esters, we're gonna start with this side. And then we're gonna name this side. And then we have the name of the functional group. So how many carbons are highlighted in red? 3. So what is the prefix for 3 carbons? Prop. Cool. And then in yellow, how many carbons are there? No! Trick question. You have to count the carbonyl carbon. 2. One person said that, but I don't know who it was, so nice. Killing it. Okay, so then we have F. And then what is the suffix for an ester? It has an "and" in it, but there's more to it. No, the anhydride was the double ester looking thing. NO8. So when we're naming esters, the anoate is the suffix for an ester. And then we're going to start with whatever's attached to the oxygen. So in this case, we have a propyl group. So we have propyl, bless you, because it's not part of the parent. And then we have the S and OH because we have an ethyl group on the carbonyl carbon side. Questions, comments? Are we kind of okay with that? Okay. So then to finish the session, let's do this one. So what is the first thing we're going to name? Which side, the oxygen or the carbon side? Hint. The side attached to the oxygen or the side attached to the carbonyl? The oxygen. Cool. So how many carbons do we have here? 2. So we have ethyl. And then on the carbonyl side, how many carbons do we have? 3. So it's prop. And then the actual ester group, what suffix does it have? NO8. Yay! And yes, these are just flip-flops of each other. Okay. Questions? Anything? If not, then I will let you go, and I will see you in lecture. Happy Monday. Oh, I have no idea. Oh, okay. So there is